In this lecture, we want to look at the basics of analyzing AC circuits. The overall impedance of components connected in series is the sum of the individual impedances. Just like in DC circuits, the voltage across a series network divides into fractions that are proportional to the respective impedances of the components connected in series. The formula for calculating the voltage Vx across an element or a number of elements connected in series is Vx equals Zxe over Zt. Zx is the total impedance of the elements across which we want to calculate the voltage. Zt is the total impedance of the elements in the whole series network. E is the voltage that appears across the whole series network. In this example, we are given a circuit and we want to calculate the overall impedance. Because this is a series network, the total impedance is the sum of the individual impedances, and we obtain it as 6.325 ohms at an angle of minus 18.43 degrees. And this is the corresponding impedance diagram. It shows the three impedances that make up the circuit, as well as the overall impedance, which is a vector sum of the individual impedances. In this example, we are given a series network and we are required to calculate the voltages VR, VL, VC, and V1. The first step is to obtain the total impedance of the network, and it works out as 10 ohms at an angle of minus 53.13 degrees. The voltages VR, VL, and VC are voltages across single elements. Therefore, we substitute the impedance of the element in question, the total impedance, as well as the total voltage across the series network into the formula for voltage divider rule. We obtain the voltages as VR equals 30 volts at 83.13 degrees, VL is 45 volts at 173.13 degrees, VC is 85 volts at minus 6.87 degrees. V1 appears across two elements that are connected in series. Therefore, the impedance across the elements in the question is the sum of the two impedances, which is J9 minus J17. We substitute into the formula for voltage divider rule to obtain the voltage V1, and we obtain it as 40 volts at minus 6.87 degrees. In the third example, we are given a series network. We are required to A, calculate the total current I, B, find VR, VL, and VC using Ohm's law, C, determine VR, VL, and VC using VDR, D, calculate the average power delivered to the circuit and the total power factor. We notice that the voltages VR, VL, and VC appear across two elements each. Therefore, the first step is to determine the overall impedances of the respective pairs. For the resistances, the overall impedance is 10 ohms because the resistances are in series. For inductances, the total inductance is 0.1 henries because the inductances are in series. The corresponding impedance is J37.7 ohms. For the capacitances, the overall capacitance for the two capacitances in series is 100 microfarads. The corresponding impedance is minus J26.53 ohms. The total impedance of the circuit is the sum of the individual impedances of the pairs. Therefore, it works out as 15 ohms at an angle of 48.16 degrees. The total current flowing into the circuit is source voltage over total impedance, and we obtain it as 1.33 amps at an angle of minus 48.16 degrees. To calculate VR, VL, and VC using Ohm's law, we substitute the respective impedances into the Ohm's law equation. We obtain VR as 13.3 volts at minus 48.16 degrees, VL 50.14 volts at 41.84 degrees, VC 35.28 volts at minus 138.16 degrees. To obtain them using VDR, we substitute the respective impedances into the VDR equation. We obtain VR as 13.3 volts at minus 48.16 degrees, VL 50.14 volts at 41.84 degrees, VC 35.28 volts at minus 138.16 degrees. We notice that the answers that we obtain from Ohm's law are the same as the answers that we obtain when we use VDR. The total average power is equal to EI cos phi, where phi is the phase difference between the supply voltage and the total current. It works out as 17.74 watts. The total power factor is cos phi, and it works out as 0.667 lagging. As exercise, prove the Kirchhoff's voltage law for the network. The overall admittance for components connected in parallel is equal to the sum of the individual admittances. In terms of impedances, the inverse of the overall impedance is equal to the sum of the respective inverses of the individual impedances. For two impedances in parallel, Z1 and Z2, the total impedance may be calculated using the formula ZT equals Z1, Z2 over Z1 plus Z2. In a parallel network, the total current divides into fractions that are proportional to the admittances of the respective branches. In terms of impedances, the fractions are inversely proportional to the impedances of the respective branches. The formula that can be used to calculate the current Ix in a branch with impedance Zx is Ix equals Zt over Zx by It. It is the total current into the parallel network. Zt is the overall impedance of the parallel network. For two branches in parallel, the currents can be designated as I1 and I2. The corresponding impedances are then designated as Z1 and Z2. The currents in the two branches can then be calculated as I1 equals Z2 IT over Z1 plus Z2, and I2 equals Z1 IT over Z1 plus Z2. In this example, we are given a parallel network. We are required to determine the input admittance, calculate the input impedance, and draw the admittance diagram. The input admittance is equal to the sum of the inverses of the respective impedances. We obtain it as 0.2136 Siemens at an angle of minus 20.56 degrees. The total impedance is equal to the inverse of the total admittance. We obtain it as 4.68 ohms at an angle of 20.56 degrees. And here is the admittance diagram. It shows the respective admittances as well as the total input admittance, which is a vector sum of the individual admittances. In this example, we are given a network with two branches in parallel. We are required to use the current divider rule to find the current flowing in each branch. We use the current divider rule formula for two branches in parallel. We obtain our currents as I1 equals 1.644 amps at an angle of minus 140.54 degrees. I2 is 6.625 amps at an angle of 32.33 degrees. In the third example, we are given a parallel network. We are required to A. Determine the total admittance. B. Find E and IL. C. Determine the equivalent parallel circuit as far as the terminal characteristics are concerned. D. Determine the equivalent series network as far as the terminal characteristics are concerned. We can partition our network into three parallel branches. The branches are the resistance branch that consists of two resistances in parallel, the inductance branch that consists of two inductances in parallel, the capacitance branch that consists of two capacitances in parallel. Let's go on to determine the impedances of these three branches. For the resistance branch, the impedance is 8 ohms. For the inductance branch, we first determine the overall inductance of the two inductances in parallel and then calculate the corresponding impedance. We obtain it as J 4 ohms. For the capacitance branch, again, we first calculate the overall capacitance and then calculate the corresponding impedance. We obtain it as minus J 10 ohms. The total admittance of the network is equal to the sum of the inverses of the respective impedances of the branches. We obtain it as 0.195 Siemens at an angle of minus 50.194 degrees. The supply voltage is equal to the supply current over the total admittance. We obtain it as 61.538 volts at an angle of 50.194 degrees. The current through the inductance branch is equal to the supply voltage over the impedance of the inductance branch, and we obtain it as 15.385 amps at an angle of minus 39.81 degrees. To obtain the equivalent parallel circuit, we express the total admittance in rectangular format. We get the value 0.125 minus J 0.15. Therefore, the circuit is made up of a resistance in parallel with an inductance. The resistance is equal to the inverse of the real part and is therefore equal to 8 ohms. The reactance of the inductive part is equal to the inverse of the imaginary part and is therefore equal to 6.67 ohms. From the frequency and the value of the reactance, we obtain the inductance as being equal to 6.67 millihenries. To obtain the equivalent series network, we calculate the total impedance of the network and express it in rectangular format. In this case, we are given the total admittance. Therefore, the total impedance is equal to the inverse of the total admittance, and it works out as 3.283 plus J 3.939. Therefore, the equivalent circuit consists of a resistance in series with an inductance. The resistance is the real part and is equal to 3.283 ohms. The inductive reactance is the imaginary part and is equal to 3.939 ohms. From the reactance and the frequency, we can work out the inductance and we obtain the value 3.939 millihenries. As exercise, compute the power delivered to the network as well as the power factor. We have an exercise here where we are required to calculate the total admittance and obtain the equivalent parallel network. I will leave this exercise for you to do on your own. Generally, in the analysis of AC networks, series parallel networks are reduced using the same approaches as those used for reducing DC networks. Secondly, KVL and KCL are applied using the same procedures as those for DC networks. In both cases, complex impedance is used in place of resistance. In this example, we are given a series parallel network. We are required to A. Find the total impedance of the network. B. Compute I1, I2, and I3. C. Verify KCL at one of the nodes. We identify three branches in the network. The first branch comprises of the resistance R1. Its impedance, denoted as Z1, is equal to 10 ohms at 0 degrees. The second branch consists of the resistance R2 and the inductance XL1. Its impedance, denoted as Z2, is equal to 3 plus J4, which is equal to 5 ohms at 53.13 degrees. The third branch consists of the resistance R3, the inductance XL2, and the capacitance XC. Its impedance, denoted as Z3, is equal to 8 minus J6, which is equal to 10 ohms at minus 36.87 degrees. The total admittance of the network is equal to the sum of the inverses of the impedances of the respective branches. We obtain it as 0.316 Siemens at an angle of minus 18.43 degrees. Therefore, the total impedance is equal to the inverse of the total admittance, which is equal to 3.16 ohms at 18.43 degrees. The current I is the source current. Therefore, it is equal to the source voltage times the total admittance. We get it as 63.25 amps at minus 18.43 degrees. The currents I1, I2, and I3 are the currents flowing in the three respective branches. We know the voltages across the branches and the impedances of the branches. Therefore, we can use Ohm's law to compute these currents. I1 works out as 20 amps at 0 degrees, I2 40 amps at minus 53.13 degrees, I3 20 amps at 36.87 degrees. I will leave you to verify KCL as an exercise and on your own. We are given here another series parallel network. We are required to A. Calculate the currents I1 and I2. B. Find the voltage VAB. We identify two branches in the network. The first branch consists of R1 and XL. Its impedance, denoted as Z1, is equal to 5 ohms at 53.13 degrees. The second branch comprises of R2 and XC. Its impedance, denoted as Z2, is equal to 10 ohms at minus 36.87 degrees. The two branches are in parallel. Therefore, we can obtain the total impedance of the network using the formula for two impedances in parallel. We get the impedance as 4.472 ohms at 26.56 degrees. The current I is the source current, therefore it is equal to source voltage over total impedance. It works out as 22.4 amps at minus 26.56 degrees. The currents I1 and I2 are obtained using the Ohm's law. I1 works out as 20 amps at minus 53.13 degrees, and I2 is 10 amps at 36.87 degrees. VAB is calculated as the difference between the potentials VA and VB. VA is equivalent to the voltage across the 4 ohm inductance. VB is equivalent to the voltage across the 6 ohm capacitance. The two voltages VA and VB appear across elements that are contained in two respective series portions of the network. Therefore, we can calculate them using the voltage divider rule. VA works out as 80 volts at 36.87 degrees. VB works out as 60 volts at minus 53.13 degrees. Therefore, VAB equals VA minus VB, which is equal to 100 volts at minus 73.74 degrees. In this example, we are given a series parallel network. We are required to A. Calculate the total impedance. B. Compute the currents I1 and I2. C. Find the average power delivered to the network and the power factor. We identify three branches in the network. The first branch comprises of the resistance R1. Its impedance Z1 is equal to 4 ohms at 0 degrees. The second branch consists of R2 and XC. Its impedance Z2 is equal to 11.4 ohms at minus 37.87 degrees. The third branch consists of XL and R3. Its impedance Z3 is equal to 10 ohms at 36.87 degrees. The three branches are connected to form a series parallel network. The total impedance of the network is equal to Z1 plus Z2 parallel Z3. It works out as 10.68 ohms at 1.5 degrees. The current I is the source current. Therefore, it is equal to the source voltage over the total impedance. It works out as 9.36 amps at minus 1.5 degrees. I divides into I1 and I2. Therefore, I1 and I2 can be obtained using the current divider rule. The two currents work out as I1 6.27 amps at minus 36 degrees, I2 5.5 amps at minus 38.72 degrees. The power factor is equal to VI cos phi, where phi is the phase difference between the source voltage and the source current. It works out as 93.6 watts. The power factor is equal to cos phi. The phase difference is very small, therefore the power factor works out as being equal to 1. Another example, we are given a series parallel network. We are required to calculate currents I1 and I2 and then verify KCL at one of the nodes. I will leave you to work out this problem on your own. I recommend that you do these questions from chapter 9 before you proceed to the next lecture.